Hello, Hornets, and welcome. Today we're going to be discussing the comparison tests for convergence. And there are two tests that we're going to be looking at today. The first test is called the direct comparison test, and the second is called the limit comparison test. And they both work from a basic concept called bigger than big is big, and smaller than small is small. You see, it kind of works like this. If I know something is small, and I have something that is even smaller, then I know I have something pretty small. For example, let us say that I have um, an elephant that is smaller than a mouse. Well, that's pretty amazing. And if I look at it, I'm going to say, wow, that's smaller than a mouse. That's pretty cool. Now, if I say I found an animal that's smaller than an elephant, that doesn't do me much good because I have no comparison to work with. Sort of like this. Consider this. Let's say I have more money than Bill Gates. I'm rich, right? Keep in mind, he's got a lot of money. Now, granted, he's done a lot. He's put a lot of money into various charities and things like that, and I give him the kudos. Okay? Now, if I tell you that I have less money than Bill Gates, well, that doesn't mean anything. Bill Gates has so much money that if I have two, three, $4 million, which frankly to me is a large amount of money, well, that's not more than he has. And there's no comparison there. I can't tell how much money that is unless I have somebody closer to compare to. Okay? So, this idea of bigger than big is big and smaller than small is small is fundamental to the comparison tests we're going to do. Now, I'd like to just put up some information in order to help you understand this. All right, so I've pre-made some notes and hopefully they will make some sense to you. And it goes like this. A comparison test requires a known series, sort of like knowing a mouse, the size of a mouse, or the amount of money that Bill Gates had. Having more money than Bill Gates is the idea of having more than something that I know is big. And therefore, a comparison of a series that I know that will diverge, if I can choose a series that is smaller, it's not going to do me any good because I can't tell whether it's going to diverge or converge. But if I know a series that diverges and is smaller than the series that I am comparing, then the series that I'm comparing, being larger than the divergent series, must also diverge. Sort of like pushing it out of the way. If I have a curve like this and I have another one that's above it, it has to diverge. It has no choice. Now, if I have a series that I know converges, and I'm comparing it to a series that is smaller for every single term, then the series that I'm comparing will have to converge. That's what this is saying right here. A comparison requires a known series, one which we know either converges or diverges. So, if we want to know whether a series converges or diverges, we first select something we know such that it is either larger or smaller than the one we want to compare with. Now, if I choose a series that is smaller than the one I'm looking at, I'm trying to prove that the series I'm looking at will diverge. Notice, in order to use a smaller one, I'm working with divergence. If I'm trying to work with a series, let's say, that is larger than the one that I'm considering, so I choose a series that I know, and it's converging, then I need to make sure that the series that I'm comparing has terms that are all less, so that they will then diverge themselves, or converge themselves, excuse me. So here is our first one. This is called the direct comparison test. And this is where we choose a series that we know will either converge or diverge. Here we go. If we have a series a sub n that is less than or equal to b sub n for all n, then if we know that b sub n, the larger series, converges, the smaller series, by the direct comparison, must converge. Now, if we're looking at the a sub n and we say a sub n diverges, see how in this the a sub n is less than the b sub n? But a sub n diverging is going to force the larger series b sub n to diverge also. That is the entire idea for the direct comparison test. So, the statement smaller than small means that the continuous decreasing series of positive terms that we know converges, then a smaller continuous decreasing series of positive terms will also have to converge. Let's just go ahead and take a look at an example of this. Let's take a look at the series n equals 2 to infinity of 1 over n squared plus 1. Now, what we want to do is we want to select a pure series. A pure series is just n to a p power. All right. So if I'm looking at a p series, all I want to work with is the highest power of n. Ignore any coefficients. Ignore any sums or smaller values of n. They aren't going to do anything. So in this case, I'm going to want to compare to a p-series, and the p-series I'm going to work with is n squared. Okay? Notice how 1 over n squared is going to create terms that are larger than 1 over n squared plus 1, because that 1 is adding into the denominator, making the denominators of that right side rule larger in the denominator. Larger values in the denominator are ultimately smaller. So I can see that 1 over n squared is larger for every single term than 1 over n squared plus 1. And we know that 1 over n squared as a series will converge by the p-series. It's a p-series, and p is greater than 1, so it must converge. Here we go. Once I've got this set up, and I already know that n squared is converging, and I know that 1 over n squared plus 1 has terms, all of which are smaller than 1 over n squared, I can then conclude that the series 1 over n squared being a convergent series and 1 over n squared plus 1 a smaller series will then force that smaller series to converge. This is by the direct comparison test. Let's look at it clearly. We start by selecting our p-series. The p-series that I am selecting is 1 over n squared. That's the one I want. We know that 1 over n squared converges, and we know that every single term for 1 over n squared is larger than every single term of 1 over n squared plus 1. Therefore, we can conclude by the direct comparison test that the summation from 2 to infinity of 1 over n squared plus 1 must converge. This has been the direct comparison test. In the next video, I will be doing the limit comparison test. Thank you very much. Be well, be safe, take care, Hornets, and I hope this helps you. Bye-bye now.